Hi, I'm Charlie D'Souza, Associate Professor of Chemistry at SUNY Adirondack. I'm about to read to you an excerpt from a paper that I co-authored from back in 2004. It's Substituent Effects on the Barrier to Carbamate CN Rotation. Now, this was a paper that came about from a research project that I actually did with my classmates in my organic chemistry class. I was a sophomore in undergrad, about the same age as some of you, and this is organic chemistry, which is a subject I actually teach here now. I'm especially excited to share this part of my own undergraduate experience with you as you go through yours. Now, while this paper goes into great technical detail about this physical organic chemistry study that we've done, let me just kind of break down basically what we're looking at. All right, so we're looking at this class of compounds called carbamates, and essentially we have a carbon-nitrogen bond here that you can rotate around. You can generally rotate around single bonds, and so you go from one version of the molecule where what we call the anti-conformer, where the larger groups are opposite from each other across that bond, to what we call the syn conformer, where those larger groups are on the same side of that bond. Okay, I say larger groups, really it's higher priority, but I'm going to just call them larger groups now just for simplicity's sake. Anyway, the point is that you can typically flip back and forth between these two states, right? However, there is a resonance structure where you have some double bond character to that carbon-nitrogen bond. Now, the problem with this is that you can't rotate around double bonds. They're kind of locked that way. So the more stable this double bonded transition state is, the more energy you need to do this rotation from the syn to anti versions of this molecule. For those of you who haven't taken my organic chemistry class, Chem 203 and 204, but may have taken Chem 103, or even if you're in regular Gen Chem, Chem 111, 112, you may be more familiar with Lewis structures than with organic shorthand. So to help explain this, I've drawn the structure that was in the paper as a Lewis structure. Now, where does that double bond come from that we see in that transition state that's kind of important to this study? The organic shorthand doesn't include lone pairs, so sometimes it can be hard for people who haven't taken organic chemistry to follow along here. So what's going on is that nitrogen actually has a lone pair on it, right? For those of you who have taken Chem 103 or Gen Chem, you know that these atoms have to meet the octet rule. So even though it's not shown here, since there's only 3 bonds to that nitrogen, and therefore only 6 electrons, there must be 2 more electrons to help it meet the octet rule in the form of this lone pair. So that lone pair comes down here, okay, and contributes to what will eventually become a double bond. Now, we can't have 5 bonds to this carbon, so this the pi electrons from this double bond get pushed to that oxygen, okay, and that's why it winds up having 3 lone pairs and therefore a negative formal charge. This is where that double bond between the nitrogen and the carbon comes from, and that's what hinders the rotation between the syn and anti-conformer. You can't rotate around this bond if that bond is locked in a double bond. All right, so basically, the more stable you can make this, the harder it is to rotate around that double bond. You see an increased, increased energy barrier. That's delta G double dagger that we're measuring. That energy barrier being higher tells you that this state is more stable, and you see less rotation. Now, to really probe this effect, we ran this experiment with different substituents on this benzene ring. So now this is organic shorthand, but you have to understand a benzene ring has 6 carbon atoms connected in a ring here, and each of those has 1 hydrogen attached to them due to the fact that each carbon has 3 bonds to neighboring carbons. It has only room for 1 more bond. And so we swap out one of the hydrogens for any of these groups. The numbers next to it tell you which position the group's at. So the nitrogen over here is attached to the number 1 position. This would be the number 2 position, the number 3 position, and the number 4 position. Okay, so If you see 4-methyl here, CH3, there's a CH3 group that's substituted over here. Likewise, any of these substituents that have a 4 in front of them are at this position here. Now, the thing to note here is the electron donating and electron withdrawing effects of these groups. Now, I go into way more detail in this if you ever take my Chem 204 class, but in a nutshell, a group like a methoxy group, especially when it's in the number 4 position, all right, it has a very strong electron donating effect. In other words, the lone pairs that are on the oxygen sort of get pushed into this ring, and as a result, electron density is pushed towards this nitrogen. Okay. On the other hand, we have a nitrile group. All right. You may be familiar with its ionic form, the cyanide group. And it basically, that nitrogen that's attached to it kind of sucks electrons away from the carbon that gets attached to this carbon here. So that's what we call an electron withdrawing group. It sort of pulls electron density away from the ring and therefore away from that nitrogen. Okay, and this of course has an effect on that positive charge in this transition state. So if you have an electron donating group, it pushes electrons towards this nitrogen. So that positive charge doesn't feel so stark. It kind of stabilizes it a little bit. So it makes this overall state a little bit more stable. Okay. And if it's an electron withdrawing group, this gets less stable because now this nitrogen that's already positively charged has even more electron density being sucked away from it, thereby making it less stable. Substituent effects on the barrier to carbamate carbon-nitrogen rotation. A paper by Bradley Smith, Deanne Goodenough-Lashaw, Carlisle D'Souza, Kieran Norton, Leslie Schmidt, and James Tung. Abstract. 7 aryl-substituted T-butyl, N-methyl, N-aryl carbamates were prepared, and in each case, the barrier to carbon-nitrogen bond rotation, delta G double dagger, was determined in deuterated chloroform solution using variable temperature NMR. A linear free energy relationship is observed between delta G double dagger and the electronic stabilization effect of the substituent on the N-aryl ring. More specifically, electron donating groups increase delta G double dagger, whereas withdrawing groups decrease delta G double dagger. Interrotation about the carbon-nitrogen bond in amides, carbamates, and related systems is an ongoing topic in conformational stereochemistry that has attracted the interest of many investigators. The subject remains relevant because a very large number of biological molecules have amide bonds, and many pharmaceutical agents and polymeric materials have carbamate bonds. Thus, it is important to fully understand how structural and environmental factors control the associated kinetics and thermodynamics. In the case of amides, it is well accepted that the carbon-nitrogen bond rotation is slow because it involves disruption of a partial double bond. Furthermore, the amide ground state is more polar than the transition state, and the rotational barrier, delta G double dagger, is increased by structural and environmental factors that favor increased polarity. The mechanistic picture is not so straightforward in the case of carbamate CN rotation, where it appears that, depending on the solvent, the transition state may be more or less polar than the ground state. The literature contains a few isolated studies of substituent electronic effects on amide and carbamate rotation, but there has been no systematic attempt to develop Hammett-like free energy relationships, due in part to the lack of suitably tractable systems. The rotational barrier is often measured by dynamic NMR methods, but this can be challenging in the case of secondary amide and carbamates because the syn anti-equilibrium is so often strongly biased to one side, which makes it difficult to accurately measure line shapes and relative populations. It is usually more convenient to employ molecular systems with tri-substituted nitrogens because they have rotamer equilibria that are closer to unity. For example, this present contribution concerns a series of substituted T-butyl, N-methyl, N-aryl carbamates whose syn and anti-rotamers are defined in Scheme 1. At low temperatures, NMR signals for the different rotamers can be observed, and the rotational barrier, delta G double dagger, can be easily measured at signal coalescence. Recently, we reported that an N-aryl carbamate has a smaller delta G double dagger value than an analogous N-alkyl carbamate. We attributed this observation to the electron withdrawing nature of the N-aryl group, which attenuates the dipolar character of the carbamate ground state and induces more carbon-nitrogen single bond character. In this present report, we investigate this effect in more detail. We compare the related carbamate compounds shown in Scheme 1 and observe a linear free energy relationship between delta G double dagger and the electronic stabilization effect of the remote R group. Specifically, we find that electron-donating R groups increase delta G double dagger, whereas withdrawing R groups decrease delta G double dagger. In summary, this study shows how linear free energy relationships can be used to probe the mechanism of carbon-nitrogen rotation. The data indicates that carbamate carbon-nitrogen rotation in a weakly polar solvent involves a dipolar carbamate ground state and a relatively less polar transition state. It will be interesting to repeat this substituent study in a polar protic solvent, where the mechanism may involve a transition state that is more polar than the carbamate ground state.